Do you think you are looking at a 3D world right now? Well, you aren't. You are looking at a flat two-dimensional grid, a bunch of imaginary lasers, and a math trick that has been lying to you since 1992. Or to your parents. Let's build it from scratch, but that would be a little too straightforward for this channel. So let's get weird and make it in a pixel shader. I'm going to use ShaderToy as there is a zero setup and everything runs in your browser. What we are going to do today is called a raycaster, and it was used for games such as Wolfenstein. It is fast, efficient, and actually even challenging if you are not careful with your math. You will see what I mean in a moment. Before we can run around in 3D, or better to say fake 3D in this case, but let me use 3D for simplicity. We need a two-dimensional world. A raycaster is really just a 2D grid disguised as a 3D. At the top of our code, we define map size to 8 and an integer array called map. Every 1 is a solid wall, and every 0 is an empty floor. To see what we are doing, we dedicate the left side of the screen to a minimap using a drawMap function. It checks our screen pixel, finds the grid tile, and paints it based on our array. Finally, we drop our player in using an SDF, or signed distance function, called SDF circle. We haven't really talked about SDF yet, but for now, let me just say that in principle, it is a mathematical representation of a shape that calculates the shortest distance from any given point to the nearest surface of the shape. It's a great way to draw things in a pixel shader. Now, for the cool stuff, lasers. We see the world using raycasting. We shoot a fan of lasers, or rays, from our player's center. If a ray hits a wall quickly, we draw it tall. If it travels far, we draw it short. Pretty clever. In the code, we set a constant raise number to 40 and loop a variable a from -40 to +40. Inside the loop, we take the player's base angle, add a, and use cosine and sine to turn that angle into an x and y direction vector. To fire the rays, I wrote a shootRay function. This uses a DDA algorithm. We talked about the details before, so feel free to check out that video. It steps exactly along the grid lines, checking our map array. If tile add returns a 0, it keeps going. The second it hits 1, the loop breaks and it returns the exact distance traveled. We draw lines to those intersection points, and our two-dimensional dot now has a glowing green cone of vision. That is great for orientation, but we want the first-person shooter, not the radar. Time to cross into the third dimension. On the right side of the screen, we draw one vertical line for every ray. We take a constant wall height and divide it by our ray's distance, which is closest point .z. We use that to stretch a line vertically. For every single ray we shoot, we calculate the exact top and bottom coordinates of the wall on our screen. We then use a two-dimensional line drawing function to slide a thick blue line perfectly between those 2 points. But solid blue looks completely flat, so to make it feel genuinely three-dimensional, we take the ray's perpendicular distance and use it as a darkening multiplier. This artificially fades the walls toward black the further away they are, mimicking depth and shadows. Once the wall slice is drawn, we simply draw a green line from the bottom of the wall straight down to the bottom of the screen to create a floor, and a dark gray line straight up for the ceiling. In principle, that should be it, right? Well, do you remember, as I mentioned in the beginning, that the math can betray you? Look at this. When we run it, it looks terrible. The flat walls bulge out like a crystal ball. This is what we call a fisheye effect. Why is it happening? Because the rays at the edges of your vision travel a longer diagonal distance than the ray dead center. The code thinks that the edges are further away, so it shrinks the walls. In my code, I put a band-aid on this. Closest point z is multiplied by cosine radians of a. This artificially shortens the diagonal lines. Stand still, looking forward, and it looks okay. But let me break it for you and turn the camera. Can you see how the walls warp and swim? Unfortunately, our clever trick was not that clever. We achieved a cylindrical projection. To get through flat 3D walls, we have to throw away our angles completely. Our monitors are flat, not curved. Not necessarily physically flat, if you are thinking tens of years ago, but well, you know what I mean here. So our math needs a flat camera. Let me draw it for you. If I shoot a ray every 1 degree or so, look at the distances between the points or intersections on the far wall. They grow in size for arrays further from the center, right? That is not what we want, so we need to upgrade to vector math. Instead of a single viewing angle, we define two vectors: player direction, pointing exactly where we are looking, and camera plane, which is player direction rotated 90 degrees. This represents our physical screen inside the two-dimensional world. Multiplying it by 0.8391 sets our field of view. Back in our loop, we ditch the angle sweeping. We create camera X, scaling smoothly from -1 to +1. Our new ray direction is just normalized player direction plus camera plane times camera X. We are now shooting rays evenly through a flat plane. The final piece, we replace our old cosine hack with dot product. Dot between ray direction and player direction. Because both vectors are normalized, the dot product effortlessly extracts the true perpendicular distance to the wall, ignoring the long diagonal. We run it, and the fisheye monster is dead. The walls are mathematically perfect from every angle. It looks great, so let's add a proper movement. Shaders are stateless. Every frame, 60 frames per second for instance, the memory wipes screen. If we move, the shader forgets by the next frame. The fix is buffer A, which is a hidden texture where we paint data instead of pixels. We pack our players X and Y, an angle, into a vector tree called state, and save it into the RGB channels of pixel 00. Now, our engine has a memory. In the handle keyboard function, we read the up and down keys, turn our angle into direction vector, and update our coordinates with state XY, with direction times move amount. By the way, the third variable of our player's state, the Z coordinate, is dedicated entirely to storing our viewing angle. This is why we can turn our head using left and right. It works! We can walk, but if we keep walking, we creep straight through the walls into an infinite void. Our player is a ghost. To trap us between the walls, we need collisions. We copy our map array into buffer A and add a tile add check. This is a kinda dirty, but functional. Before we update state XY, we asked if the new coordinate hits a 1. The trick here is checking the X and Y axis independently. If X is blocked but Y is open, you slide smoothly along the wall instead of dead stopping. We also add bounce checking, so rays don't read out of bounds memory. Compile it, and the geometry is completely watertight. Let me increase the number of rays and tighten the distance among them. Look at what we built. A two-dimensional mathematical grid on the left, and a distortion-free, collision-enabled 3D perspective on the right. We defeated the Fisheye Effect, embraced true vector math, and resurrected the exact architecture of an old-school shooter. But right now, we are wandering through simply colored blocks. To make this a real game, we need texture mapping. We need pixelated bricks, metal doors, two-dimensional sprite enemies. That's an entirely different beast, so maybe next time. If you like what you saw and want to see more in the future, feel free to subscribe, like, comment, or even become a member if you want to support the channel. Thanks for watching, and ciao!